Namaskaram. In last class, we have seen that how to integrate along a surface. Today, we will discuss an application of surface integral. That is, we have to find an amount of fluid flowing across a permeable surface in a unit time. That is called flux. Solution of last homework. To understand the concept of flux, we have to introduce some basic definitions. Okay, first we have to introduce the concept orientation of a surface. There are two type of surfaces: orientable surface and non-orientable surface. For orientable surface, sphere is an orientable surface because sphere has two orientation. One is upward orientation, one is outward orientation, other is inward orientation. Okay, and similarly a plane has two orientation. One is upward orientation, other is downward orientation. Clear? So these two are orientable surfaces. Okay, so in this figure, suppose this is our surface sigma, this yellow one is surface sigma, then this sigma has two orientations, one is upward and other is downward. So this is a orientable surface. Okay. Okay, other one is non-orientable surface. For example, Mobius strip. I will explain what is Mobius strip. Mobius strip is nothing. First of all, you take a strip like this, then cut at this edge. So this top point is A, bottom point is B. Then we twist one edge 180 degree like this. Then you join it. So whenever we twist this 180 degree, B, the point B become top position. Okay. Then you join it. Okay. Now we get a strip like this. So this is called the Mobius strip. It is clear that this Mobius strip has only one surface. Okay, in the sense that suppose you are starting from this point, you are starting from this point and moving in this direction. Then what happened? Whenever you're moving in this way up to this point, then you turn 180 degree around, then you come the outside of the strip, then again you moving through the outside, again you come to this point, then again you twist 180 degree, so you go to through the inside of the strip and ending at this same starting point. That means you can cover entire side, inside and outside. There is no actually Mobius strip has no sides, only one side. Anyway, you can cover entire side without crossing the edge. But in the case of this orientable surface, you can't go to the other side without crossing the edge. Okay, so that is a difference between orientable and non-orientable surface. Okay, here you can't go the other side without crossing the edge. Here you can go all the sides of this strip without crossing the edge. Okay, so here this surface has only one orientation or only one surface. It has two surfaces in the sense that two orientation. That is the idea of orientation. Okay. Okay, next definition gives a mathematical formulation of this concept. Suppose a surface is orientable surface, then we mathematically define one orientation as positive, other as negative. Okay, let's see. Okay, suppose we have a three-dimensional surface and this is the parametric representation of the surface. That means in terms of two parameters, u and v. Okay, here we take a u and v. Anyway, this is the parametric representation of the surface. Then we consider a vector like this, dou r by dou u cross dou r by dou v. Okay, mathematically we can easily prove that this dou r by dou u cross dou r by dou v is perpendicular to the tangent at any point. Okay, that means it is always normal direction. This vector is in normal direction to the surface. That means this vector is normal to, suppose we calculate this cross product at this particular point. Then this is a vector and it is perpendicular to the tangent plane at this point. That is called normal. Okay. So by dividing this modulus of this vector gives a unit vector. And direction is same. Only we scale the vector. Okay. So now this n is a unit vector and this is normal to the surface. Either this direction or downward direction depending on the surface. Okay, and depending on the surface. Okay. Anyway, this n is a unit normal to the surface sigma. I'm not going to the proof of these things. So this is a unit normal to surface sigma. And next we are going to define the orientation of the surface sigma. Okay, how to define the orientation? The direction determined by n is called the positive orientation of the surface sigma. That means suppose suppose this n has this direction, upward direction, then we say that this is the positive orientation of the surface. And then what about the minus n? Minus n is opposite to, if this is n, then minus n is downward direction. Then we say that this is the negative orientation of the surface sigma. So we have two orientation for orientable surface. One is positive orientation, other is negative orientation. Positive orientation is determined by this vector, this unit vector n. Okay. Okay, next we will see some special cases of this parametric surface. Okay, next we will see three special type of surfaces and what about their unit normal. Okay, these are the three special cases. Z is equal to gxy, or y is equal to gzx, or x is equal to gyz. Okay, these are the three special cases of surfaces. Then what is the advantage of this special case? Suppose we consider the first case, z is equal to gxy. Then we can parameterize these type of surfaces using these two independent variables. That's the idea. Okay, because already z is in terms of x and y. So you can convert everything in terms of x and y. So only two things. Two things means they are the parameters. We can treat here we can treat x and y as instead of u and v. Okay. Similarly, suppose a surface is of the form y is equal to g zx. Then we can treat here u as z and v as x. Okay, like that. So everything is in terms of two things, that is z and x. Similarly, this case also. Okay, in this case, this is the parametric representation. Suppose z is equal to gxy. Then we can write the corresponding vector equation like this. R is equal to, instead of u we take x, xi plus yj plus some function of xy, g of xy. Anyway, this is the parametric form because it involves only two things, two variables. Okay, similarly, this is the corresponding parametric form of this case, and this is the corresponding parametric form of this case. And also we can identify the positive orientation and negative orientation of such surfaces. Suppose we consider the first case, then this is our R. So next we have to compute n. What is our n? Okay, so this is the formula of unit vector n, dou r by dou x cross dou r by dou y. Yes, instead of u and v, we use x and y. Okay, here x and y are the parameters. Divided by its modulus. Suppose we calculate this numerator dou r by dou x cos dou r by dou y for the first case, then this become, yes, this is our numerator. This cross product is like this. Then what is the meaning of this vector? Okay, then if you to find n, we have to divide with its modulus. Anyway, it does not change the sign, does not change the direction of n because it's a positive number. So what is the direction of this n? Suppose z is equal to gxy, then my question, what is the positive orientation? What is the direction of positive orientation? It is clear that whatever be the point, the n is for n, it's kth component. We have three components I, j, k. The coefficient of kth component is 1 throughout 1. That means what? That means this vector is always pointing up direction. Okay, suppose we have x, y and z coordinate, then whatever be the point, always the n means it's this value, its the coefficient of kth component is always 1. That means the vector is always upward direction. Okay, so in the case of z is equal to gxy, its positive orientation means upward direction. Upward means maybe like this. Anyway, its kth component is 1. Okay, so upward direction. And so what about minus n? If you compute the minus n, what happened? This become plus, this become plus, this become minus 1. Okay, this become minus 1. So that downward direction. So in the case of z is equal to gxy, positive orientation means always upward direction. Negative orientation means always downward direction. Similarly, in the case of y is equal to gxz, you compute this n, then you can show, it is clear that the corresponding to this value, I will show you one second. Okay, in the second case, if you compute n value, what happened? this is our numerator, dou r by dou x cross dou r by dou y corresponding to this representation. Then it's, you see the jth component, its coefficient is 1. That means this vector is always in the direction of increasing y. You got it? In the direction of increasing y. So what about the minus n? Minus n is direction of decreasing y. Okay. So similarly, in the case of x is equal to g y z, the positive orientation means in the increasing direction of x, and the negative means the direction of decreasing x. Okay. So these are the positive and negative orientation of these three special cases. Okay, because we have to discuss only these three special cases. In this course, we will discuss only these three special cases. Okay. Okay, now we are ready to define our main problem. Suppose that an oriented surface sigma is immersed in an incompressible steady state fluid flow. Incompressible means, for example, liquids are incompressible but gases are compressible. Okay, so incompressible system and steady state. What is steady state? If flow does not depend the time, then such state is called steady state. Okay, and that the surface is permeable so that the fluid can flow through it freely in either direction. Okay, find the net volume of the fluid, that is called flux, that passes through the surface per unit time. That is our main problem. Okay, here the net volume means the volume passes through the surface in the positive direction, because our surface is, okay, already we assume that our surface sigma is orientable. So we have two orientation. One is maybe one is this direction, other is its opposite direction. Okay, then the net volume means the volume passes through the surface in the positive direction. Suppose this is our positive direction. In the positive direction, minus the volume passes through the surface in the negative direction. If this is our positive direction, then this direction is negative direction. Then the volume corresponding to this direction minus the volume that passes through this direction. Okay, in unit time. That is our net volume. And the net volume per unit time is called flux. Okay, our aim is to calculate this flux. Okay, this is the formal definition of flux: the net volume of the fluid that passes through the surface in 1 unit of time. That is our flux. Okay, that's a net flux. Okay, so it is clear that the flux depends so many things. The first one is flux is proportional to the speed of the flow. Okay, it is clear that if speed is high, then the volume of the fluid passing per time is high. That's all. Okay, so flux is proportional to the speed of the flow. Then next one is fluxes varies in accordance with how the surface is oriented. That means flux depends the orientation of the surface. You got it? If suppose this is our direction of flow and surface is slanted, then what happened? Surface is like this, then it is clear that the flux is comparatively less. If the surface is perpendicular to this flow, then flux is maximum. You got it? So flux depends the orientation of the surface. Then, and one more thing is there, flux is proportional to the area of the surface. If area is high, then flux is also high. If area is small, then flux is comparatively small. Okay, so see that these are some basic observations about the flux. Okay, so to understand the concept of flux, suppose we consider a very basic case. Suppose we have a surface sigma, and suppose there is a fluid flow which is perpendicular to the sigma, which is a constant speed. Constant, suppose a speed equal to some 5 centimeter per second. So this is the speed, 5 centimeter per second. That is our speed, and speed is uniform throughout the sigma, and it is perpendicular. The flow is perpendicular. Okay, and suppose its area is not. Suppose the area of this flat surface sigma is not. Okay, let it be some 2 units its area. Then how to find the flux? What is flux? Flux is the amount of fluid flowing across the surface sigma in unit time. It is clear that we can what about the volume? The volume, suppose this is surface sigma. You think about speed. Suppose speed is the height, right? Then you think about this cuboid shape thing. Okay, so this is the volume. So volume corresponding, the height of this volume is speed, isn't it? So what about the flux? Flux is equal to speed into area. Okay, so speed into area gives the flux. But we have a problem. We have a problem is we have a surface like this sigma, but the speed is not constant throughout this sigma. Speed depends xyz because we have a velocity function. Suppose that the velocity of a fluid at a point xyz on a surface sigma is given by this formula. That means velocity depends the point. It is not throughout the same. Okay, so we have to subdivide this region, then we have to calculate flux, approximate the flux corresponding to each region, then we have to take the sum, and that approximation is better if n is very large. Okay, that is the idea of evaluating the flux. Okay, so and n be the unit normal vector towards the positive side of sigma, that is a positive orientation of sigma. Okay, then the idea is this one, to find the total flux across a surface sigma, because sometimes along this portion flow may be in this direction and this portion flow may be in opposite direction. Okay, so we have to find the net volume across this surface sigma. Okay, and also it is important that which direction the net flow is in this direction or net flow in this opposite direction, that is also important. So how to manage all these things? So first of all, we divide the sigma into n patches, sigma 1, sigma 2, etc. sigma n. So this one is first patch sigma 1, this is sigma 2, like that. Okay, with the areas delta S1, delta S2, etc. delta Sn. Approximate the volume of the fluid crossing the patch sigma k in the direction of n per unit time is equal to f dot n into delta sk. The same idea of this one, speed into area. But how to interpret this f dot n? Okay, it is clear that flux is equal to speed into area. This is nothing but area of the small patch. Next we have to identify the speed. But in this case we have to accommodate one more thing, the direction of the speed, not velocity. Only thing is the direction of the speed, because we have to take the algebraic sum. Okay, so if the flow is in the direction of n, then we take the velocity and the speed as positive, and suppose the flow is opposite to the direction of n, then we take the speed as negative. That's all. Then only we take the algebraic sum of the volume, then only we get the then only we will get the algebraic sum of the volume. Okay, so let me explain this formula in detail. Okay, so our main concept is the volume. The volume is equal to speed into area, but here we incorporate one more thing, plus or minus. Plus means speed is in the direction of n, minus means speed is in the direction of flow is opposite to n. That's all. Okay, so what about this quantity f dot n into n? F dot n is a scalar, n is a vector. Okay, so this is a smart picture. This is our kth patch corresponding to sigma. And what about f dot n? So suppose this is our direction of n. This vector is, this big vector is n, positive oriented vector. Suppose here the velocity is in this direction. F at this point is like this. So that means the velocity is in this direction. To find the flux, first we have to find the velocity in the direction of n. To find the velocity corresponding to n, we simply compute f dot n into n. Okay, so f dot n into n gives the component of velocity in the direction of n. So we have to find only speed. To calculate the volume, we need only speed with the sign. So how to find the speed with the sign? So how to find the speed? We know that speed is equal to modulus of velocity, isn't it? Modulus of velocity gives the speed. So you consider the modulus of f dot n times n. So this is equal to modulus of f dot n, because this is n is unit vector, so its modulus value is 1. So this is modulus of f dot n. We know that speed is always positive, so modulus of f dot n is always positive, but we need signed speed. That's why we consider just f dot n. So f dot n is a numerical quantity, maybe positive, maybe negative. If it is positive means what? F dot n is positive means the its magnitude, its modulus value is the speed of the flow, and sign determines the direction of the flow. If f dot n is positive, that means the flow is in the direction of n. You got it? If f dot n is negative means the flow is opposite to n, and modulus of f dot n gives the speed of the flow. That's the idea. That's why we consider this. Okay, so this is the idea. The sign of f dot n determines the direction of flow. A positive value means the flow is in the direction of n, and negative value means it is in the opposite of n. You find, if suppose you have to find the speed, then you simply take f dot n. That's all. If you find the exact speed, then you take f dot n without sign. That's all. Because f dot n, anyway, f dot n is a numerical value, maybe positive number or negative number. Then why we remove this modulus? That is because we have to find the net fluid flow, net volume. For example, suppose we consider this is our sigma 1, this is our sigma 2. Suppose in this patch, suppose flow is upward direction. And also you assume that in this patch flow is downward direction. Okay, we have to find the net flow. So to find the net flow along the positive direction of the surface, suppose this is our positive direction of the surface. So to find the net flow, we have to first of all compute the flow at this point and flow at this point, take the difference. Okay, automatically the minus sign accommodates in this f dot n. F dot n accommodates that minus sign because here flow is opposite direction. So f dot n involves speed with the sign. You got it? So you simply take the sum of these two. No need to put minus sign. Automatically minus sign inside f dot n. Okay, that's advantage. Suppose you consider instead of f dot n, suppose you take modulus of f dot n. Then what happened? Then you manually put minus sign whenever the direction of flow is opposite. That is difficult to evaluate. Okay, then how to approximate the total flux? You take the flux at this patch plus flux at this patch plus etc. Take the flux on n patches and take the sum. Okay, then take the algebraic sum. But there is another thing. Suppose you consider a kth patch. We know that the velocity may be different in each point, but this patch is very small. So we assume that is an approximation. We assume that the velocity on this patch throughout same, and the velocity is equal to f of x k star, y k star, z k star. This point is an arbitrary point from this kth patch. Okay, if this patch is very small, this approximation is better. Okay, so what about the approximation of total flux? That is equal to f dot n into, that is the velocity corresponding to first patch, into area, that is delta S1. So this is the flux corresponding to sigma 1 plus f dot n times delta S2. This f dot n is from the second patch. Okay, f dot n times delta S2 plus etc. up to nth one. So this is an approximation, and this approximation is better. So this is the approximation of total flux, and this approximation is better and better whenever the size of these patches are very small. That is possible when n is very large. So total flux is equal to limit n tends to infinity. You got it? So the total flux is equal to limit n tends to infinity, sigma k is equal to 1 to n f of x k star, y k star, z k star dot n times delta s k. Okay, this representation is familiar. This is familiar to us. What is this? Yes, in terms of integration. Yes, this is exactly double integral delta sk. Delta sk is the area of the patches of the surface sigma. So this integration is along the surface sigma. You got it? So this is a surface integral. Double integral over surface sigma. What is the inside? Inside is f dot n. Sorry, f dot n. F dot n. So this is exactly our surface integral. So we can evaluate our total flux using this surface integral formula. Double integral over sigma f dot n ds. Yes, that is equal to double integral over sigma. Simply we can write f dot n. by removing x, y, z. We can simply write f dot and ds. Okay. So this is the formula for evaluating total flux. The next one, how to evaluate this surface integral. Okay. The general formula for evaluating the surface integral is this one. But in this course, we have to discuss only 3 special cases, not the general form. That's why we put a star. This is not in the syllabus. Okay, so anyway, this is the general formula. Anyway, we have to discuss the 3 special cases of the surface. So we will discuss that 3 cases. Okay, how to evaluate flux over such surfaces. Okay, these are the 3 special cases. Suppose sigma is the surface of the form, either this one, or this one. And suppose we rewrite our equation sigma like this: gxyz equal to 0 by taking, this is very important, by taking whatever be the form, this is the idea, by taking g to the left side of the equation. Okay, suppose this is the case, then what is g? G is nothing, z minus g of xy. Okay, if this is the case, then what is capital G? Y minus g of zx. Taking g to the left side, that's the idea. Okay. And what about R? R is the projection of the surface sigma on the coordinate plane. In this first case, here coordinate plane is xy, because here x and y are independent parameters. Okay. So in the second case, what is the coordinate plane? The plane determined by z and x, that is xz plane, like that. Okay. So that is the idea, determined by the independent variables of G. If sigma has positive orientation, then the total flux phi is equal to, this is the formula, W integral over sigma f dot and ds, and this is equal to, this is our normal integration. This is a surface integral, this is normal integration, W integral over R is the region in a coordinate plane. Okay, f dot del G dA. And why this del G? Because this is our general formula, W integral over R, f dot dou R by dou U cross dou R by dou V dA. We can show that, we can prove that dou R by dou U cross dou R by dou V, in the case of first form, what is our R? R equal to xi plus yj plus gxyk. This is the parameter representation. Instead of u and v, it is x and y, that's all. So we can show that this dou R by dou x cross dou R by dou y is equal to del G. Okay, this part we can show that dou R by dou x cross dou R by dou y is equal to del G. That is very easy. You can simply find this cross product and it is clear that is del G. We know how to evaluate the gradient del G. They are equal. Okay, that's the idea. Anyway, this formula is very important. If z is any of these 3 form, then we can compute this phi using this formula. This is our normal integration. If this is the case, then R is the projection of the surface sigma in the xy plane. If the second case, then R is the region, it is a projection to the xz plane, that's all, of the surface sigma. Okay. Also, the interpretation of phi is important. Suppose this is the case, suppose our surface is z is equal to gxy. Okay, then we know that the upward direction is the positive orientation and downward is the negative orientation. We calculate this phi with respect to the positive orientation. Okay, you got it. So suppose phi is positive, we compute phi for a particular surface of this form, and phi is positive. Then what is the meaning? The meaning is the net flow is in the direction of n. That means net flow is in this direction of n. Okay, suppose phi is negative, then what is the meaning? That means net flow is opposite to the n, that is in downward direction, net flow. Maybe some portion flowing upward direction, but majority is in downward direction. So net is in downward direction. That's the interpretation of sign of phi. Okay. Okay, for example, suppose z is equal to gxy, then how to write g? G is nothing, z minus g. Okay, this is, so z minus gxyz, so this is our g. So what about del g? Del g is the gradient. First you differentiate capital G with respect to x, then it is that is dou g by dou x. There is a minus sign, and okay, one mistake is there. Actually, this is only gxy. There is no z, isn't it? Because z minus gxy. So this is z minus gxy. Okay. So del g equal to minus dou g by dou xi. Next one is, actually what is del g? Del g is dou g by dou xi plus dou g by dou yj plus dou g by dou zk. This is the formula of gradient. And what about dou g by dou x? You differentiate this expression with respect to x, that is same as minus dou g by dou x. Okay, and if you differentiate with respect to y, this capital G become minus dou g by dou y. And what is the derivative of capital G with respect to z? That is 1. That's why this term become 1k. Okay, so again, what about dou g by dou x? We can replace, we know G is same as z, so we can replace this G by z. So the final representation is minus dou z by dou xi minus dou z by dou yj plus k. So this is the gradient of z is equal to gxy. Okay, so if sigma is z is equal to gxy and oriented upward direction, then this flux become double integral over r f dot del g dA. Here del g is in upward direction. It is clear this is positive k. Okay, suppose sigma is same this form, and suppose oriented downward direction. Oriented downward direction, then this surface integral is like this f dot, instead of del g we use minus of del g. Okay, this is minus k, that means in downward direction. That's only difference. Similar results exists for all these two cases. Okay. Okay, for this second case, y is equal to gxz, and suppose it is positively oriented, then this flux is equal to double integral r. R is the projection of the surface sigma to xz plane. Okay, f dot del g. What is del g? Del g is minus dou y by dou xi plus j minus dou y by dou zk. Okay, if it is negatively oriented, this become plus and minus and plus. Similarly, you can find the corresponding formulas for x is equal to g by z. Okay. Okay, first problem. Let sigma be a portion of the surface z is equal to 1 minus x square minus y square that lies above the xy plane, and suppose that sigma is oriented up, it is positively oriented. Find the flux of the vector field, this one, across surface sigma. Okay, and what is this? Z is equal to 1 minus x square minus y square. This is actually, it's a paraboloid. Okay, and what is the maximum value of this z? Because z is equal to 1 minus x square plus y square. We know that x square plus y square is always greater than or equal to 0. So the maximum value of z is corresponding to x square plus y square is 0. Okay, so whenever x square plus y square is 0, z equal to 1. Okay, so maximum value of z is 1. That's why the shape of the parabola is like this. Okay, it is clear that suppose z equal to 0. When z equal to 0, this is x square plus y square equal to 1. So this circle, the circular shape. Okay. So anyway, we have to find the flux. We know how to evaluate flux. Okay, it is clear that this surface is of the form z is equal to gxy. Z is equal to gxy. So we can use that formula. Okay, our flux phi is equal to double integral sigma f dot and ds. That is equal to double integral r f dot. This is our del g. Okay, this is positive direction, so we use del g. This is our del g. So next we have to substitute f and this del g. We get double integral r. F is xi plus yj plus zk. And what is dou z by dou x? Here dou z by dou x is minus 2x, but there is a minus sign, so this becomes 2xi. Similarly, this is plus 2yj plus k dA. Next, our aim is to evaluate this double integral over R. And what is R? R is the projection of the surface to the coordinate plane. Here the coordinates are x and y. They are independent variables. Okay. So we have to integrate this. We have to integrate this sum on this green circular region. Okay. So we know how to evaluate our double integral. So better we use the polar form because it's a circular region. Okay. Okay, by taking the dot product, this becomes 2x square plus 2y square plus z. And it is given that z is equal to 1 minus x square minus y square. That is our surface. Okay, so by substituting this value for z, so this becomes this quantity plus 1 minus x square minus y square. So what happened? This becomes 2x square minus x square, that is x square, So this is equal to double integral over r x square plus y square plus 1 dA. Okay. Okay. So next we are going to integrate this using polar form. Okay. So what is our r? R is this circular region with radius 1. So what is the range of r? What is the range of r? We know the polar form is x is equal to r cos theta and y is equal to r sin theta. So what is r? R is varying from 0 to 1. So this is the variation of r. And what about theta? We have to cover this entire green region. To cover this entire region, theta should varying from 0 to 2 pi. Now we can set up this integral in polar form using the substitution. Okay, and similarly, what about dA? dA is r dr d theta. Okay, now everything is ready. Then this integral become, okay, integral 0 to 2 pi, that is the range of theta. This is range of r 0 to 1, and this x square plus y square become r square. Okay, x square plus y square is always r square, so r square plus 1 r dr d theta, and that is equal to, okay, so this become r cube plus r dr d theta. By integrating this first part, by integrating with respect to r and substituting upper limit and lower limit, we get 3 by 4. So next we have to integrate the 3 by 4 with respect to theta. So this become 3 by 4 into theta and 0 to 2 pi. So this become 3 pi by 2. So the total flux across the surface sigma in the direction of n is 3 pi by 2. Okay, it is okay. The yes answer is 3 pi by 2. Okay, it is clear here. The sign of this flux is positive, isn't it? It's a 3 pi by 2. Then what is the meaning of this plus sign? So this plus sign means the net flow across the surface is in this direction. Net flow. Maybe some portion the direction of flow is this one, and some other portion direction of flow is downward direction. But net flow is in the direction of upward direction, because we evaluate this flow using the positive orientation of the sigma. Okay, suppose you calculate the same flux using the negative orientation of sigma, then what is the difference? The only difference is instead of 3 pi by 2 you will get minus 3 pi by 2. So what is the meaning of this minus 3 by 2? Because we use the negative orientation for sigma. Negative orientation for sigma means downward direction. So we evaluate the flux using the downward direction, but flux is negative. That means what? That means the flux is opposite to negative orientation. That means flux is upward direction. So anyway, we get the same flux. Okay, only difference in the sign depending on the orientation of the surface. That's all. Next problem, find the flux of this field xi plus yj plus z square plus 4k through a 3 by 2 rectangle in the plane z equal to 1. You consider the plane z equal to 1. It's a infinite plane. On the plane we consider rectangle 3 by 2. One side is 3, other side is 2. It does not matter the position of this rectangle. Whatever the position, we get the same answer. So that is not a matter. Oriented in the negative z direction. That means we oriented this rectangle in the downward direction. Okay, that's the difference. We oriented the surface in the downward direction. We have to find the total flux. So we evaluate the flux with respect to the downward direction. That's all. That is the difference. Okay. So what is the formula? Okay, this is the formula. Phi is equal to double integral r f dot minus del g dA. Instead of del g, we take minus del g, because here the surface is oriented in the negative direction. So we take minus del g. Okay. Okay, so what is minus del g? Minus del g is dou z by dou xi plus dou z by dou yj minus k. This is minus del g. And what about dou z by dou x? Here dou z by dou x is 0 because there is no x variable. Similarly, dou z by dou y also 0. So minus del g become minus k, isn't it? So this expression become, this is our f dot minus k dA. Okay, so again this is equal to double integral over r. By taking the dot product, this become minus of z square plus 4 dA. Again, what about z? We have to integrate. This is our surface sigma. So on the surface sigma, z value is throughout 1. So on the surface sigma, this z is equal to 1. So this becomes 5. So double integral over r minus 5 dA. And this is equal to minus 5 double integral over r dA. And what about this quantity? Double integral over a region dA. What is this? Yes, this is exactly the area of the region R. Okay, double integral over R dA is nothing. It is the area of the region R. What is the area of region R? What about the projection of the sigma? Sigma is a rectangle on the z equal to 1. So its projection is also a rectangle. Whatever with the position of this rectangle, its projection is always a rectangle. Isn't it? So what is the area of this rectangle? That is 3 into 2, that is 6. So this become minus 5 into 3 into 2, that is 6. So minus 30. So minus 30 is the flux. Then what is the meaning of this minus 30? Because flux is minus 30, so its sign is negative. So negative sign indicates that the net flow is opposite to our orientation. Because now we oriented the surface in downward direction. But flux is negative. That means the total net flow is in upward direction. You got the idea? Because we oriented the surface in negative direction, that is downward direction. Then we evaluate the flux using that assumption. So we get the flux as negative. That means the net flow is opposite to our orientation. Our orientation is downward. That means the net flow across this surface sigma is upward direction in 30 units. Okay, that's our observe. That is a interpretation of this minus sign. So this is the idea. This is our surface sigma. We oriented the surface sigma in downward direction and flux is negative. That means the net flow in the positive direction of Z with the 30 units. That's the idea. Okay. Yes, these are the homeworks.